Before we start this lecture, let me take you through what we have discussed so far in this particular module, especially in the last lecture. What we have been discussing is that we are trying to see in situations of elections where the candidates are fighting with each other to get elected, what could be the choice of agenda of the candidates, how the voters will vote, who will win in equilibrium, and to understand these questions and to give the answer to these questions, we are basically applying this framework of game theory and in particular Nash equilibrium. And this particular framework has a name, it is called the Hotelling's model. So, this is Hotelling's model of electoral competition. And what we have discussed so far is that there are, to make it simple, there are two candidates who are trying to win in the election, and there is a continuum of voters. Each voter has a favorite position in the sense that each voter has a particular policy which he or she will like to see implemented. What the candidates want is that they just want to win, and there can be three kind of situations. One is the candidate is winning outrightly. Second is that he is not winning outrightly, he is having a tie with the other candidate in the first position. So, this is the second preferred option for a candidate. This is not the best option to happen to a candidate. And the third alternative, which is the worst alternative for a candidate, is that he loses. So, that is the worst thing that can happen, and this is the preference ordering. You win outrightly, that is the best. Second is that you are in the first position, but you are having a tie, and third is that you lose. And as I said, that every voter has a favorite position, and these favorite positions are distributed in a continuous manner over this line. So, every number in this line will represent the favorite position of at least one voter, and M is the median of all these numbers. Now, since it is a game between the candidates, so each candidate will announce some policy and try to get as much vote as possible. If he gets more than half of the votes, he wins. And based on that, we have seen that we can construct the best response functions for the candidates. This is the best response function of, suppose, player 1. We have seen that this can be represented as so, this is the best response function of player 1. Basically, what is happening is that if player 2 announces something here to the left of M, player 1 has to then, if player 1 wants to win, has to announce something here on this range, because if he announces something in this range less than x2, so this is x2, then all these votes will go to x2, and which is greater than half because M is here. So, to win, player 1 must announce something more than x2, but merely announcing more than x2 will not do. if player 2 announces something here, player 1 announces something here suppose, then a middle point between x1 and x2 is falling in this case here to the right of m, which means all these votes will go to player 2, and since this point is to the right of m, player 2 will get more than half of the votes and player 2 will win. So, for player 1 to win, player 1 should ensure that x1 plus x2 divided by 2 is less than m, and from that we get this condition that x1 should be less than 2m minus x2. So, if this is m, this is 2m minus x2, x1 should be less than that and greater than x2. So, x1 should be in this range, and in only that case player 1 will win. If player 2 is announcing a position just equal to m, then in no circumstance can player 1 win this election, because if he announces something to the left, he is getting these votes less than half. If he is announcing something here, he is getting these votes again less than half. So, by announcing something other than m, he will of course lose. So, if player 1 announces m in this case, then he can at least tie with player 2, and that is the best thing that he can do in these circumstances. So, that is why if player 2 is announcing m, player 1 is also announcing m. And the third situation is like the first situation. Here x2 is greater than m, then like before x1 should fall in this range, and this point is given by twice m minus x2. If player 1 announces something here, then he will lose. If he announces something here, again he will lose. So, he will announce something in this range. That is why we have got this condition. So, this is the best response function of player 1. Similarly, we can find out the best response function of player 2, which we can write as follows. So, this is just replacing x1 by x2 and x2 by x1. And now the next task is that we try to plot these two best response functions and try to see what is the point of intersection or points of intersection, and those point or points will be the points of Nash equilibrium. Suppose this is the x1 axis and x2 axis, and we want to plot this best response functions. First is this, that x2 is less than m, then what we are having here is that x1 should be greater than x2. x2 is less than m, so we are talking about this range. Suppose this is the point mm, this is the point 2m to m. What we are having is that x1 should be greater than x2. So, I can imagine this line, which is the 45-degree line, x1 should be greater than x2 means we are taking points to the right of this line. Do I take all the points all the way to infinity? The answer is no. x1 should be less than 2m minus x2, this. So, I need to plot this line 2m minus x2. How will this look like? This is a straight line with a vertical intercept of 2m. So, it will start from here and a slope of minus 1. So, this line will go through these 3 points. So, this is the line x1 is equal to 2m minus x2. X1 should be less than 2m minus x2 in this case. So, I cannot take points on this line, but I have to take points to the left of this line. So, this is the best response function in this case, that x2 is less than m. If m is x2 is equal to m, I have got x1 is equal to m. So, I pick up this point is on the best response function, and if x2 is greater than m, this is the case, then x1 should be less than x2, x1 should be less than x2. So, all these points will be included, and x1 should be greater than 2m minus x2. So, all these points to the right of this line should be included. So, we have this shaded, horizontally shaded region as the best response function of player 1. Similarly, I can show that if x1 is less than m, I have got x2 should be greater than x1. So, all these points will be included, and x2 should be less than 2m minus x1. So, all these points will be included, and similarly the last part will be depicted by this shaded region. And if x1 is equal to m, x2 is equal to m. So, again we are picking up this same point in between. So, what is the crux of the story? The crux of the story is that we are having this shaded region, both kind of shades, as the best response function of these two players. Horizontal shades represent the best response function of player 1, vertical shades represent the best response function of player 2, and they are not having any intersection point except for this central point. So, this is the only Nash equilibrium. MM, which means that both the voters, both the candidates are announcing the same position as their policy position. If they announce the same policy position, then obviously the voters will be equally divided between these two candidates, which means no one is winning outrightly, it is a tie. At the same time, no one is losing either. So, this is the Nash equilibrium situation here, the only Nash equilibrium. When Hotelling, the economist Hotelling, proposed this model, he was basically analyzing the US political map, and his conclusion was that in US, obviously, as you know, there are two major parties, the Republicans and the Democrats, and there are other small parties, but they are not very significant. So, the fact that we have two important parties, that is reflected in this model also. There are two parties, and the conclusion of this model is that they are going to announce the same policy. Now, in real life, of course, the Democrats and the Republicans do not announce identical same policy positions, but as many political observers feel that their political positions or their announcements of what they will do after elected to the office are not radically different from each other. Maybe there will be some differences, minor differences, but most of them, most of these two parties announce positions which are largely similar and which is reflected by this MM. So, that is how the economic model or game theoretic model is having a real life counterpart. This fact that we are having a Nash equilibrium at MM, we have proved this by constructing best response functions and all. But the same demonstration could have been done in a more direct fashion. If you remember, in the case of Bantra model, we have tried to show that there also CC equilibrium could have been shown in a more direct argument. Here what one can do is that first show MM is a Nash equilibrium, not the, is a Nash equilibrium, and second step will be to show no other Nash equilibrium exists. So, both of them together will mean that MM is the only unique Nash equilibrium. The first part is not difficult to prove. We have given the argument already. If I chooses M, J cannot choose Xj not equal to M and be better off. So, if the other player is choosing M, I have to choose M. If I do not choose M, I lose. If I choose M, of course, there is going to be tie. Tying is better than losing. So, by deviating, one is not better off, one is in fact strictly worse off. So, this is a strict Nash equilibrium. So, first part is proven. What about the second part? No other Nash equilibrium exists, which means that if Xi Xj is there where Xi is not equal to M, Xj is not equal to M, then this is not a Nash equilibrium. How do we prove this? Well, let Xi is not equal to Xj. There can be two possibilities. One is Xi is not equal to Xj, and the second is that Xi is equal to Xj. These two exhaust all possibilities. Now, if Xi is not equal to Xj, and it so happens that suppose there is a possibility here that one of them, let us say I, is losing, and the second is that nobody is losing, which means this is a tie. We have to consider these cases and we have to show that none of these cases can be a Nash equilibrium. If none of these cases can be a Nash equilibrium, obviously we have exhausted all possible cases. So, the only Nash equilibrium that remains is that Xi is equal to Xj is equal to M, that is the only Nash equilibrium. Now, if Xi is not equal to Xj and one of them loses, can that be a Nash equilibrium? The answer is no. And the reason is that I who is losing will then be deviating and be better off. For example, he can at least announce M. If he announces M, then either he is going to have a tie, because if xj is also is equal to M, then there is going to be tie. Or he can outrightly win, because if xj is not equal to M, then I by announcing M is going to win the election. So, both of these possibilities are better than losing. So, there is profitable deviation and there is a tie. How can there be a tie if xi is not equal to xj? This is the case where there can be tie, where this distance is equal to this distance. The distance between xi and M is same as distance between M and xj. In this case, there is going to be tie. Now, again this is not a Nash equilibrium, because either of the candidates can choose to announce M and win outrightly. Each of them can have a better option of announcing M. If any candidate announces M, he is winning outrightly, which is better than tying. So, again deviation is profitable. So, this is not a Nash equilibrium. What can be the other possibility? Possibility B is that xi is equal to xj. Now, if xi is equal to xj, it means that it is a tie. Both the players are announcing the same position, so it is a tie. Now, if there is a tie, is this a Nash equilibrium? The answer is no, because remember we have ruled out the possibility that none of them is equal to M. If none of them is equal to M, then what it means is that they are having a tie somewhere here. So, here xi is equal to xj, or somewhere here, does not matter. So, from here also we can find at least one profitable deviation, that any of them announces M. Suppose xi, instead of xi, I announces M, then he will win outrightly. So, we have exhausted all these possibilities and we have seen that none of them is a Nash equilibrium. So, the only Nash equilibrium we are left with is the MM Nash equilibrium. So, it is a unique Nash equilibrium. Let us now look at some other properties of this Hotelling's model. One assumption of this model is that the preference of the voters was symmetric. Now, this is a particular assumption, but it may not be very realistic. It may happen that a voter may dislike the candidate to his left more than the candidate to his right. So, he can have a stronger dislike for leftists than for rightists and vice versa. And we are going to show that that is not going to change the conclusion of the model. So, this is the exercise. Voters' preferences are asymmetric. Specifically, suppose each voter cares twice as much about the policy differences to the left of her favorite position than about policy differences to the right of her favorite position. How does this affect the Nash equilibrium? So, here the story is the following. Suppose there are these two candidates and they are announcing x1 star and x2 star, and we know these voters will vote for him and these voters will vote for him. What happens of the voters in between? Suppose I take the middle voter, this is x1 star plus x2 star divided by 2. In the assumption so far with the symmetric preference, this voter was indifferent. He could either vote for this person or this person. Now, with this new assumption, he will not be indifferent. What is being said is that if this fellow is having the same distance as this fellow, x1 star is having the same distance as x2 star, his dislike for x1 star will be twice as the dislike for x2 star, which means that this person is going to definitely vote for x2 star. So, if I have to find out which voter will be indifferent between x1 star and x2 star, how can I find that person out? This will be given by a person here. Suppose this is x1 star divided by 3. So, I am dividing up this difference between x1 star and x2 star into 3 equal parts. After this first part, I am getting this point, x1 star plus twice x2 star divided by 2. Now, for this person, the distance between this person and x1 star is half of the distance between his position and x2 star. And since for equal distance the dislike is twice for the leftist candidate than to the rightist candidate, here since the differences are twice for the rightist candidate, his dislike for x1 star and x2 star will be the same, which means that all these voters will vote now for him and all these voters will now vote for him. So, this is the difference that we have in the setup. And question is, does this affect the Nash equilibrium? Remember, the Nash equilibrium in the previous model was MM. Question is, does this still remain a Nash equilibrium? We can proceed as we have done just now in the direct argument case. First, we show that this is a Nash equilibrium. And the procedure is very simple. If someone announces M, what can the other guy do? The other guy can announce more than M, he loses. So, if he announces x2 and x1 is at M, then all these voters he is getting more than half of the distance, but still this other fellow at M is getting more than half of the total votes and he is winning. And no matter how close you come to M, this fellow is never going to win or tie with the other candidate as long as his position is more than the other person's position. Similar argument can be made for any position to the left of M. So, the argument that was offered before, that if the other person is offering M, announcing M, any candidate cannot do any better but to announce M, still holds, which means that this remains a Nash equilibrium. So, the second step was that to show that no other pair is a Nash equilibrium where xi is not equal to M or xj is not equal to M. Here also the argument will be roughly the similar. They can be different or they can be same. If they are different, then any of the candidates who is losing, suppose a candidate is losing, can do better by announcing M. Either he will tie or he will win. If they are tying, x1 and x2 are different and they are tying, then again any of the candidates can go and announce M. and he will win outrightly. And the third possibility is that these two candidates are announcing policies which are same. If their announcements are the same, then they are having a tie. If they are having a tie, then any of the candidates can deviate and announce M and win. So which means that no other Nash equilibrium is possible. Look here, this fact that my hatred for the leftist candidates is twice does not make any difference. So the result that MM is the unique equilibrium is a robust result. We can look at other aspects of this model. For example, here the model had only two candidates, and we also had the requirement that any candidate who is a candidate cannot have the option of staying out, not competing. If you are a candidate, you are contesting, but this is not very natural. A candidate, for example, instead of contesting may like to opt out. In particular, it may happen that if he contests, he will lose for sure. In that case, why should he contest? He will better stay out of the contest. So, if we give that option to a candidate, does the result remain the same? So, opting out. That is not contesting. Question is, does it change the result? And the answer to that question is again no. The result that we had MM as the unique equilibrium stays even if we have this additional option for the candidate to stay out. The proof is the following. The fact that someone is not contesting can change the result by two ways. It can happen that in equilibrium one candidate is contesting, the other candidate is not contesting. So, he is opting out. Or it can happen that both the candidates are not contesting the election. That can also make a difference, because that is something which we did not consider before. Question is, one candidate opting out or not contesting is not equilibrium. Why we are saying that one candidate not contesting not equilibrium? The reason is that if I am not contesting, the other candidate is contesting, then the other candidate is winning. And what are my preferences? My preferences are the following. First, outright win. So, this is very obvious like before. Second is tying in first place with other candidates, maybe not outright win. Third is opting out. I am not contesting. And fourth is losing. Now, third is worse than second. If third is worse than second, then the candidate who is not contesting, he can do better by contesting and at least, for example, announce M. If he announces M, then either he wins or he ties, which both of them are better than opting out. So, one candidate contesting, the other candidate not contesting cannot be an equilibrium. Can it happen that both candidates not contesting, can that be an equilibrium? And the answer is again no. If both the candidates are not contesting, that cannot be an equilibrium, because from the point of view of each candidate, opting out is worse than winning. So, each of the candidates will think that better than opting out, I should enter the race and win outrightly. So, again that is not an equilibrium. So, the only equilibrium that can happen is that both candidates are contesting, and if both the candidates contest, we are back to the old situation where both the candidates are contesting, and we know that the only equilibrium is this equilibrium. So, the fact that a candidate has the option of staying out, not contesting, is not making any difference to the result. Let us now try to extend this model. Suppose we have 3 candidates. So, instead of 2, then does the result still hold? So, this is the exercise that we are interested in. So, this is the exercise. Suppose there are 3 candidates and each candidate has the option of staying out of the race, which he regards as better than losing and worse than tying for the first place. This is something which we have already seen. Show that the game has no Nash equilibrium if less than 1/3 of the candidates' favorite positions are equal to the median favorite position. So, this is one additional assumption, and second is that less than 1/3 voters favorite is equal to M. So, how to prove that in this particular situation that there is no Nash equilibrium? But before we start to prove this, let us look at the significance of this assumption. Here is M, and less than 1/3 of the voters have their favorite position at M, which means that more than 2/3 voters So, if I take the total number of voters whose favorite positions are to the left or to the right of M, then their number will be more than 2/3, because less than 1/3 are having their favorite position at M, which means that more than 1/3 of the voters' favorite positions will lie to the left and will lie to the right, because this M is dividing the total number of voters into 2 equal halves, and the total is more than 2/3. So, in each half there will be more than 1/3. So, this is something which we have to keep in mind. This is something which we are going to apply later. Now, how to prove this, that there is no Nash equilibrium in this case? What we are going to do is that we are going to do it step by step. Firstly, we prove that there is no Nash equilibrium in which none contests. This is the first proposition. Second is that no Nash equilibrium there cannot be a Nash equilibrium where only one candidate is contesting, the other two are staying out. Thirdly, contest. If more than one candidate contest, then there can be Nash equilibrium only if there is a tie between the candidates. So, what we are saying is that suppose there is a Nash equilibrium, in that Nash equilibrium more than one candidate has entered the race, then there can be such Nash equilibrium only if between the candidates who have entered the race there is a tie in the first place. Fourthly, we are going to propose that no Nash equilibrium if if there are only two candidates who are contesting the elections, then that cannot be a Nash equilibrium. Fifthly, we show that if there are three candidates, all the three have entered the race, then there cannot be a Nash equilibrium in which they have chosen the same position. So, what are we left with? What is the only possibility of Nash equilibrium? That if choose positions not same as M. So, it means that not same. It means that is it possible that all the candidates are entering the race, they are choosing different positions, maybe two of them are same and one is different. Can that be a Nash equilibrium? We are going to show that if all the three candidates enter the race and choose position not same, then this is not Nash equilibrium. So, what we have done by all these 6 steps is the following. Let me go through the logic once again. We have ruled out all possibilities basically. First, we have said that there is no Nash equilibrium if nobody is contesting. So, which means that it leaves out the possibility that there can be Nash equilibrium if one candidate is contesting, 2 candidates are contesting, or 3 candidates are contesting. By 2, we are ruling out the first possibility that there is only one candidate contesting. Then we are saying that if suppose there are more than one candidates who are contesting, then there can only be a tie between them. By the fourth proposition, we are saying that there cannot be a Nash equilibrium where only 2 candidates are contesting. So, that leaves the possibility that all the 3 candidates are contesting and there is a Nash equilibrium. By the fifth proposition, we are saying that if 3 candidates are contesting, then there cannot be a Nash equilibrium where their positions are the same, they are choosing the same position. So, the only possibility that remains is that all the candidates are contesting and they are choosing positions which are different, at least one of them is different, and by sixth proposition we are ruling that out also. So, in sum we are ruling all possibilities of Nash equilibrium, which means that there is no Nash equilibrium. So, that was the proof. We shall stop here in this lecture. To finish, what we have done is that we have looked into different aspects of this Hoteling's game. We have seen that in the Hoteling's game, if we have 2 candidates and the standard assumptions, then MM is the only Nash equilibrium where each candidate is announcing the median position as the policy decision. We have seen that if we change the assumptions, like if we take into account the asymmetric preferences, or if we bring in the assumption of opting out by the candidates, then also the result holds. However, if we have 3 candidates and an additional assumption that less than 1/3 of the voters have their favorite positions at M, then the result no longer holds. In that case, there will be no Nash equilibrium. We shall pick up the thread in the next class. Thank you. What is the equilibrium in the Hoteling's electoral competition game? The equilibrium is at MM, where M is the median favorite position of voters. So, which means that half of the voters have their favorite positions to the left of the median and half of the voters have their favorite position to the right of the median. Of course, there could be some overlap at median also. So, to be more precise, half of the voters have their favorite positions either less than M or equal to M, and half of the voters have their favorite positions either equal to M or more than M. Why this is an equilibrium? So, we have 2 candidates here. It is just like the Batra game. If a candidate announces M as his policy, the other candidate cannot deviate from M and be better off. And the reason is very simple. If someone is announcing M, suppose player 1 is announcing M, if 2 is announcing somewhere here as his policy, then all these voters, this is the halfway mark between this position and this position, all these voters will vote for 2 and all these voters will vote for 1. But these voters are more in number than these voters. So 1 will win here if 2 announces something to the left of M. Similarly, if 2 announces something to the right of M, again 2 will lose, and the same logic holds for 1 also. If 2 announces M, 1 cannot announce something other than M and win. So given any player is announcing M, the other player's best action will be to announce M. So therefore MM is a Nash equilibrium. However, it is unique also. What is the reason why this is an unique? Suppose we take any pair, okay, so x1 x2, okay, and suppose x1 and x2 are not equal to M. So each of x1 and x2 is different from M. In this case, either one is losing. If one is losing, then what one can do is to announce M, and that will make one the winner. If there is a tie here, then also one of them could go to M and announce M and be the winner. So this cannot be a Nash equilibrium. Can there be a Nash equilibrium where the positions are like one is M, the other is x2, where x2 is not equal to M? This is again we have seen is not a Nash equilibrium, because 2 is losing here. So the best thing for 2 to do is to announce M rather than announcing X. So therefore all other cases of pairs of announcements where the numbers are different from M, they are not Nash equilibrium. If candidates have the option of not contesting, which is preferable to losing, and worse than tying in the first place, what is the equilibrium? So not contesting is an option. Our claim is that here also MM remains the Nash equilibrium, and the reason is this: what not contesting, when not contesting can make a difference. If one does not contest in equilibrium and the other contests, or both do not contest. These are the cases where not contesting this option makes a difference. Otherwise, both the players are contesting. So we are back to the old game in that case. Can these two be equilibrium positions? So let us think about this. One is contesting, the other is not contesting. If the player who is not contesting sees the game, then he knows that the other player contests, and if there is a single player who contests, then the other player wins. So it is better for this player to contest and maybe announce the same position as the first player. Then there will be a tie, which is better than not contesting. Both do not contest, again cannot be an equilibrium, because any one of them can contest and win the election outrightly, which is worse than not contesting. So these are not equilibrium. So, therefore, not contesting this option does not make any difference. Thank you.